Hi, I'm Dr. A.J. Kumar, PhD. We're reading Artin 2.10, the Correspondence Theorem. Oh, you know what? I did go and highlight the forward reference, or the backward references. I didn't put where they were because the fucking junk on my fucking desk. Alright. Jesus Christ on the fucking Jesus. No, fuck. Anyway, so let me actually let's go through and do that. The stupid fucking journal program, yeah, the pen was doing its fucking stupid malfunction thing again. Okay, so I didn't see this one. Blue. Just why? Oh wait, it might have... I got really annoyed and just killed the program, and so it might have deleted all of my annotations, I think. Yeah, it did. Okay, so we're going to have to go through and do the forward references again, because the fucking pen wasn't working. Okay. This program is just... I just hate computers so much. I mean, I hate them. I just hate them with every fiber of my heart. Everything about computers is evil and wrong. Computability, computation, is really beautiful. It's really interesting. It's wonderful. Computers, the way the CIA has created the modern computing environment, is just a travesty. I mean, and we need to be a lot more vocal about speaking out against what the CIA has done to computing by making things like Linux and PDFs, the internet as a CIA operation. Say we have the Correspondence Theorem. Let's see. Correspondence Theorem. Oh wait, that's the subject of this section, so let's not do that. Okay, okay. 258. Remember, this gets referenced a lot. There we go. Let's just look through. I don't see much else. I'm sure I missed some stuff. All right. All right. Okay. Let's go through with the pen and mark where these are. So. Oh, and then the counting formula. That's what I was thinking about. Counting formula. Really? I hate this program so much. Counting formula. That's from 2.8. That's 2.8.8. Son of a bitch. Okay. Zoom all the way in. And let's switch to, this is 2.8. This is too big. 0.8. It's page 57. And this is, oh yeah, the order of, this is just Lagrange's theorem, basically. The order of a group is the order the order of a subgroup times the index, which I'm just going to call x of H, which is a subgroup of G. There we go. Okay. 2813 That's page 58. And what does this say? This is a bunch of, it's kind of the same type of theorem as the counting formula. They're kind of all the same theorem, same ideas. Let's just keep going. Example 2.5.13. That's page 50. And this is a homomorphism from that. This was the thing I wanted to go over on my own. And maybe in Revelations 13 I'll go over this because I couldn't quite wrap my head around this. And then 2.5.15 is, I guess, the kernel of this homomorphism. I didn't really see what the systematic way to solve this was. This is page 51. That was the problem I was having, is I'm not seeing what the system is where you go from start to finish. 2.10.4, which is just above. Here, you know what, I will highlight that and just 2.10.4. I don't see any new terminology. I guess correspondence theorem. So maybe I'll highlight that in yellow. It's the correspondence theorem. Okay. So let's go through and then. Anyway, so let G to G be a group homomorphism and let H be a subgroup of G. We may restrict phi to H, attaining a homomorphism, phi restricted to H from H to G. This means we take the same map phi but restrict its domain, so by definition if H is an H, then here's some glowy notation. I understand what this means. This is not like an equivalence class or something like that. For fuck's sake, why doesn't it remember the ruler? There's some stupid setting somewhere I gotta fucking change. Why doesn't the program do exactly what I want without me telling it to do that? Okay. For clarity. Yeah. Clarity. Anyway, the restriction is a homomorphism because phi is 1, and the kernel of phi bar H is the intersection of the kernel of phi with H. Sure. Yeah. Let's just kind of run through this really quickly. So the identity element is in H. So phi of 1 goes to, so let's call this phi H of 1H. This is 1 in G. Okay, then phi H of that looks more like rho, but oh well. Phi H of H prime. Well, that's still going to be just from the fact that phi is a homomorphism. Phi H of H times phi H of H prime. That looks fine. And then, is there another rule of homomorphisms? I guess it has to send inverses to inverses, but yeah, so phi, yeah, there's never a point where you have to leave H, it looks like. Phi H of H inverse is phi H of H. Alright. Yeah, this all looks fine. And these facts are all inherited from the fact that phi with no subscript is a homomorphic on curly G. There. Anyway. It's clear from the definition of the kernel the image of phi bar H is the same as the image phi H of H. Correct, okay. The counting formula may help to describe the restriction. This is, I consider this to be Lagrange's theorem. Corollary 2813, so that was page 58. Okay. The order of the image divides both the order of H and the order of G. If order of H, so of curly G, so this is the target space, so because the image of a homomorphism is a group. So the order of the image divides both the order of H and the order of G. If the order of H and the order of G have no common factor, i.e. their greatest common divisor is 1, then the image just has to be kernel. Then the image just has to be the order of the image of phi H would have to be 1, because that's the only possible divisor. So phi of H is equal to 1, so H is contained in the kernel, so H is contained in the kernel of phi, or in other words, H is equal to the kernel of phi H. Okay. Okay, so if the image of a sign homomorphism phi from Sn to plus or minus 1 has order 2, if a subgroup H of the symmetric group Sn has odd order, it will be contained in the kernel of sigma, the alternating group An of even permutation. So if a subgroup, oh, that's interesting. So if you have a subgroup of the symmetric group that has odd order, it will be contained in the kernel of the order of the image. Okay. Let's think about this for a second. And I looked over very quickly Dummett and Foote, and it has a lot of going through really specific examples with specific groups, and so we're definitely going to go over that. Artin, the exercises have a lot of examples like that. But I like how explicit and really verbose Dummett and Foote is. This is more like a Rudin-esque book, and Dummett and Foote is more of a Munkers-esque book. And so the really Rudin-esque book, which I couldn't find a PDF for, was called Algebra by Nathan Jacobson. But anyway, there will be a link to buy this book down below, by the way. Okay, so the image of the sign homomorphism. Okay, let's walk through this logic. So, the sign homomorphism from any symmetric group, the sign function is a homomorphism. The image has order 2. Okay. Therefore, the sign homomorphism restricted to some subgroup of the symmetric group has. So if you take the sign homomorphism, okay, let's write this out in my paint. Let's write, fuck off. Let's write out this logic. Oh God. I don't know what the hell I did to my color palette. Anyway, so So we have our sign homomorphism from Sn to plus or minus 1. Okay? The integers. Okay, let's suppose H is a subgroup of Sn and the order of H is odd. Okay? Our previous logic just says that, okay, and then we're going to take sigma restricted to H of H. We're going to look at its image. Okay. The order of this okay, the order of this is either 1 or 2. Okay? Okay. So we have to pick between those two. Because okay, we're going to use some wonderful glowy notation. You love this. So this is the order of phi restricted to H of H, so the order of this image divides the order of H, which is not even, then phi restricted to H, or sigma restricted to H of H is equals 1. Okay, and the only subgroup of order 1 is, so therefore sigma sub H of H is equal to just the set containing 1. Okay. Okay. Which means, therefore, this is a common symbol for therefore. Therefore, H is contained in the kernel of sigma, and which is equal to an. So therefore, yeah, H is a subgroup of an. So all permutations. Okay. Here's what it is. An odd order subgroup of Sn contains only, so therefore even, that's the logic. This is AA30 that we're working on. I hope I have the correct thing up. Yeah, okay. Okay, so right. So a permutation that has even order may be odd or even. Okay. (210)(4). Let phi from G to G be a homomorphism with kernel K, and let H be a subgroup of G. Denote the inverse image phi inverse of H by H. Then H is a subgroup of G that contains K. Okay? Yeah, it has to. Because curly H contains 1, and so phi inverse of curly H will contain phi inverse of 1, which is the kernel of phi, or which is K. If H is a normal subgroup of G, then if curly H is a normal subgroup of curly G, then non-curly H is a normal subgroup of non-curly G. If phi is surjective, okay, so let's just pretend that, okay, that this is kind of an interesting caveat, this if phi is surjective thing. And I'm wondering what happens if you break this constraint. Whenever you see like a two-way constraint, so if x then y, and then if y and z then x, and I'm like, well, what happens if you have y and not z? Does x break? Can you come up with a counterexample? And almost certainly yes. Okay, so let's think about this. So for example, let phi denote the determinant homomorphism from GLN R to R times. The set of positive real numbers is a subgroup of R times. Phi, R times, this is a multiplicative group of real numbers. Okay. This is R dot, maybe in wider notation. The set of positive real numbers is a subgroup of R star. R star is the normal way you say this is R star. That's the normal way you say this. The set of positive real numbers is a subgroup of R star. It is normal because R star is abelian. Its inverse image, the set of invertible matrices with positive determinant, is a normal subgroup of GLN. Huh? Proof. This proof is simple, but we must keep... Okay, wait. Okay, let me zoom out so I can read this. Sorry. Here, you know what? Just so that you can read it too, I'm going to be nice for a moment, and I'm going to turn off the ridiculous, obnoxious slideshows so that you can read this. Okay, because I can't read it if it's that big. Okay, because I can't, like, yeah, when I read like a whole sentence or a whole paragraph at a time, and when it's that, maybe I need to get a smaller monitor, I'm not sure. Anyway. Or maybe move, like, walk backwards. All right. Okay, let phi from G to G be a homomorphism. Then H is a subgroup of G. So this is saying that you can pull back a subgroup. Okay, here, let's... Okay. This is saying... This is saying we can pull back a sub... Okay, so first of all, if we pull back curly G, how do we do this? Curly... If we pull back curly G, we're obviously just going to get G. Right? This is just by definition of the pullback. The first claim is that we can pull back an arbitrary subgroup. How do I do a curly H? just pull back an arbitrary subgroup, take an arbitrary subgroup of G, an arbitrary subgroup of G, pull back this H, is a subgroup H, subgroup of G. Okay? Okay. Okay. That's the next claim. The next claim is K is a subgroup of H. Okay, I'm a little bit weary about this, but this is obvious because curly H will contain curly 1. Curly H will contain curly 1. And so if you pull back curly H, it will contain the pullback of 1, which is the kernel of phi. So that makes sense. Okay, and then it says if H is a normal subgroup of curly G, then H is a normal subgroup of G. So if phi is surjective, okay. Then it says, okay, I need a better H. This is the standard notation for normal subgroup, is this triangle. H is a normal subgroup of G implies H is a normal subgroup of G. Okay? If phi is surjective, if phi is surjective, and if H is a normal subgroup of G, then curly H is a normal subgroup of curly G. Here's how you do it. There. It's a normal subgroup of curly G. God. I'm just not, my mind's not there right now. I think I gotta, this is gonna take me a while, isn't it? Alright, how am I on 6? Oh my god, okay, there's no way I can get through this. Let's just, let's do a first pass at this, and then maybe, we'll see. Let's just keep going for a little minute. For example, let phi denote the determinate homomorphism. Okay. Oh, that's interesting. Okay, I understand this paragraph. So what it's saying is that if you can, so he was using this this fact as in an interesting way. So what he's saying is we have a group G ln of R, which is not abelian, but we can put a homomorphism. I think that's the standard way you denote homomorphism. A homomorphism from G ln R to R, identify a normal subgroup of R, okay, identify a normal subgroup of R, so R plus, let's call this, okay, and then pull back the homomorphism to get the G Ln plus, let's just call it that, of R. Okay, and then this will be a normal subgroup of GLNR. I like this diagram approach. This Lang uses this type of thing a lot. Alright. Okay. Okay, I need to take a break, and we're going to come back and read the proof. So, start here. Alright. Alright, that's what we're going to do when we come back. Oops. I'm Dr. A.J. Kumar. I will see you in the next video, or in the remainder of this video. I got to take a break. Hi, I'm Dr. A.J. Kumar, PhD. We're reading Artin 2.10, which is on the Correspondence Theorem. And I actually didn't really know what this theorem was, so I botched a tape trying to do this yesterday, where I just had some brain fog, and so I read like a paragraph in, and I spent half an hour reading a paragraph. It was like reading the same sentence over and over and over again, and I would hear the words, but it wasn't. You know that feeling where you're like listening to someone talk, but you can't, and you hear every word and you can understand it, but, or like if you're reading a really boring story or reading a really boring book, and like you hear it, but you're not like paying attention and assembling some, a story in your mind. That's kind of what it was yesterday. But I did figure out some of the stuff that, like, I did work through some of the logic, more complicated logic, and so what I'm going to do is take this what I'm going to do for the time being, I'm going to take these notes that I'm doing, and I might do this for the, I don't think I'm going to go back and do this for the past videos, but I do have a lot of the notes saved, not all of them, and take the notes that I'm doing, if I'm working out some logic on the side, and I'll put those up on my locals, just so that there's something there for people. I don't know how valuable these barely legible handwritten notes are to people, but anyway, this what's the date today? 2021 10 10. Alright, okay, and I'll try to put those notes up on my local. There's a problem. I think locals is fucking gay and kind of sucks. So I'm going to build something similar, obviously not a clone, because locals fucking sucks, and so I wouldn't build a clone of it. But I'm going to build something for myself that kind of accomplishes the same thing, where I can put content behind a paywall and have like a community. And that's going to be in the OPHTDBD thing. But that's going to take me a while, so I'll use locals for the time being, but locals fucking sucks. It's just, like, on a technical standpoint, it's just really hard to use. It's really poorly programmed. Like, Dave Rubin did not hire good tech people. It was written by retards. Anyway, we're reading 2.10. Oh, and I wanted to mention other books. I'm not going to open up Amazon, but there are a couple other books that we're going to start integrating into this. Let me write these down. These are things that you should buy and get in the mail, so that when we start, if you're following this playlist, so that when we start reading them, you have the books. One is called, let me find it. It's Representations and Characters of Groups. vectors of groups by James and Liebeck. I have no idea how to pronounce Liebeck, but I'm just guessing. Then another one is, I think it's just called Abstract Algebra by Dummett and Foote. And then there's one that's just called Algebra, I think, by Lang. Then another one that maybe we'll go over. It's called, I think, Linear Representations. This one is a long way off. Representations. So that here, I'll number them. This is 1. This is maybe 2. This is 3 in terms of when I will get to them, and this is like 50. Of finite groups. By Serre. So, well, we'll see. But Abstract Algebra by Dummett and Foote, this book is like, this one I want to go over this because this is like really verbose and has a lot of really specific examples that it walks through. So I like that one. I'm actually I actually kind of am liking Artin more and more the more I'm reading him. And this seems like one of these sections that the argument is actually quite, there's a lot of dense logic here. So, and I think I mentioned this, I had some brain fog yesterday when I was trying to work through this, so I've worked through some of it, and I botched a take, because I was just, reading the same sentence over and over again and not understanding what it meant, and it wasn't that I didn't understand the words, it's just my brain was not working. But I had worked through some of the logic yesterday. Anyway, let's read. So actually, what I want to do is kind of zoom out, and there's, by the way, a link to buy this book. It's Algebra by Michael Artin. There's a link to buy it down below. As always, I've already done the thing where I mark up the forward references or the backward references, mark where they are. So it's about this thing called the Correspondence Theorem. And what it is, so here's what it is. It says, let phi from G to curly G be a surjective, and it emphasizes surjective, group homomorphism with kernel K. There's a bijective correspondence between subgroups of curly G and subgroups of non-curly G that contain K. And the correspondence is defined as follows. Right, it's just defined as its image, and then, yeah, so you can go with image and inverse image. Okay. And then he has a few examples here. And then he's also going to go back to that example about the homomorphism from S4 to S3, which I was confused about, and I want to go over that example a lot more. And this is going to go along with Revelations 23. I want to put that in the description. Rev 23 GitLab draft Revelations 23. I got to work on OP-HTTPD today. I don't think it's actually that hard. It's just let's get some stuff going. Anyway, let's. Okay, so this makes sense. Or I don't see why it's true. Right? It's not obvious to me that this is true, but the statement makes sense and it sounds plausible. So, but you know, I worked through some of the logic yesterday during the botch take, and it was it's actually it was pretty dense. So let's just get started reading it. So I'm gonna do this. Okay. So let phi from G to G be a group homomorphism, and let H be a subgroup of G. We can take a restriction to H and obtain a homomorphism phi H from H to G. This means that we take the same map phi. So maybe we can do a two-pass reading of this and let's just kind of read it through and try to figure out the larger structure of his argument, and then we can go back and fill in the details. And I think the previous sections have been pretty light reading so far, where we could just read it linearly, and I think this is one of these sections that has so much detail in the arguments that we have to do a multi-pass reading. So let's go through, and I've already done like half a pass on my own. I might publish that video, or maybe I'll append it to the end of this or prepend it. I'm not sure. We'll see. Anyway, let phi from G to G be a group homomorphism, and let H be a subgroup of G. We may restrict phi to H, obtaining a homomorphism phi H from H to G. Right. So we can take restrictions, and the kernel is just defined in the obvious way. So this is just a standard way you take a restriction of a function in math. So that makes sense. So the kernel of phi bar H would be the elements of H that map to 1 under, which would be the kernel, right. This is just true from the definition of the kernel. Yes, which is what he says in the next sentence. Okay. The image of phi H is the same as the image phi of H under the... Okay, that's correct. The counting formula, so this is the counting formula, this is the, I think my notes from yesterday got deleted, and so I gotta be sure to save my work regularly, because I think it doesn't prompt me to save my work, if my unsaved work, when I quit the program. Anyway, so the counting formula was, it's Lagrange, I just think of it as Lagrange's theorem, which was that if you have H is a subgroup of G, then the order of G is equal to the order of H times the number of orbits of H in G, and there's the same number of left orbits and right orbits for every subgroup. Every subgroup has the same number of left orbits and right orbits. It's forced by this formula even. The orbits, the left and right orbits are the same precisely when the subgroup H happens to be normal. Okay, and we're going to see more about normal subgroup. But the number of orbits is called the index, or Ix, of H subgroup G. And Artin uses this silly glowy notation, which is G colon H. And I absolutely hate when you have an asymmetrical relationship and you use symmetrical notation to refer to it. I think that's the peak of glowy retardation. I hate that. So here's a rule. If you have an asymmetric relationship, your notation needs to be asymmetrical. Okay? And if you have a symmetrical relationship, so like equals, this is good notation because it's symmetrical. Your notation should reflect the logic of what you're talking about. Okay? And then this makes it very clear I'm talking about an index. This is the letter, sorry about my handwriting, is the letters Ix, index. That's a standard word for, that's a standard shorthand for index in the computing world. index of H, which is a subgroup of G. That's what less than means in the context of group theory, is subgroup. Okay, anyway. Right, the order of, yeah, so corollary 2, 8, 13, that's page 58, and probably one of the bullet points, let me just find it, 58. Yeah, so one of the bullet points is that, so we have, okay, yeah, so, okay, this was what I was working out at the beginning of last time. Oh yeah, I was working through the logic of example 2.10.13. Okay, maybe I should write down what I was working on. So this was example 2.10.13. 2.10.3. Okay. But this corollary 2.8.13. So these notes are going to be out of order. In the future, they'll be in more linear order, but we can work on that. So 2.8.13. 2.8.13. The third bullet point. So it says let phi from G to G prime be a homomorphism of finite groups. That's important. It says the order of the image of phi divides the order of G and the order of G prime. Don't you love this notation? Okay, and I don't remember the logic of that, but this is the way you use theorems in math, is you can't remember the logic of why something is true. You can go look it up, but you use the theorems as sort of an abstraction layer over the logic. Or as we worked out this, it's more of a promise that we worked out, that somebody else has worked out the logic, and that it's true. That's really what what the word theorem means. So anyway, theorem means inescapable conclusion. That's what it means. Anyway, so the order of, so our general structure of the argument, let's kind of read it quickly, and then maybe it'll be easier to read the structure. Okay, so he starts with the homomorphism. He says we're taking a restriction, and we talk about the kernel first of all, and then we talk about the image, and that's always a thing in algebra. Whenever you talk about a map, you talk about its kernel and its image. Okay, so the counting formula, the order of the image divides both H and G. Okay. So if the order of the image divides both H and G, okay, and then this example, you know what, I am going to just append what this take to the last take from yesterday, and I worked this out yesterday. I don't want to work it out again. It's at the top of the notes. I worked through the logic here. Okay, and then 2.10.4, I think this was me just working out what the statement of this theorem was, I think. Okay, I think this is the statement of 2.10.14. I don't know why I'm saying 14. And then this is the little example afterwards. Okay. So phi from G to G curly G be a homomorphism with kernel K, and let H be a subgroup of G, denote the inverse image by H, then H is a subgroup of G that contains K. If H is a normal subgroup of G, curly H is a normal subgroup of curly G, then H is a normal subgroup of G. If phi is surjective and H is a normal subgroup of G, so this surjective thing is catching me off guard. I don't understand why that would be important. Okay, but surjective, something like this where you have, I think I mentioned this yesterday, where you have X implies Y, and then Y and Z imply X. I'm like, well, why is the Z there? Okay, so the two conditions are almost equivalent. And I guess that's this correspondence theorem. And then, right, and this was a cool idea, which was if you can come up with a homomorphism from a non-abelian group into an abelian group, actually you can always do that homomorphism by looking at the projection of any group onto its abelianization. Because every group you can make it abelian by factoring out something called its commutator subgroup, which is the set of all words that are like X, Y. So if XY is equal to YX, let's suppose we impose that restriction, then that's equivalent to saying XY, X inverse, Y inverse is equal to 1. Okay, and so if we come up with if we invent a fake group, we define this as the current, this is going to be the logic of quotienting, which is you can just say, you can factor out a relationship by like this. How do you say? You invent a homomorphism into a fake space, and you say this is the kernel of the homomorphism, and we define the new space as the image of that homomorphism. Okay, and we say this is the kernel of the homomorphism is all words like this. Well, then the new group is going to be abelian because it's going to have the property that the image group is going to have the property that xy is equal to yx. So, right, you can reason. This is kind of where math gets cool, which is where you form relationships between two spaces and you use properties of one space to force properties in another space. This is really where we're kind of starting to get to cool, interesting parts of the logic. Anyway, so I'm not going to look at the proof of this for a moment. I want to see kind of what the larger scale argument is. Okay, correspondence theorem. And then I want to see this example. Okay, group S3 has 6 subgroups, 4 of them proper. Okay, so I understand what the correspondence is. And I don't understand why the surjective thing matters. I kind of want to look at that and figure that out, because that's going to bother me. Subgroups of order 8. Okay, I really want to okay, so concerning the fourth bullet, which is the bijectivity of the correspondence. We're going to go back to the root, which is this surjective, injective stuff. Okay, and then the last bullet is an exercise, but that doesn't look too hard, which is probably why it's an exercise. Okay. I'm more interested in this proof down at the bottom. This looks like the more interesting proof than this one up here. This doesn't, god damn it, this one does not look like a very difficult or interesting proof, but the one down below of I guess that's why it's a section, because it's kind of an interesting and important theorem. This is actually kind of surprising. This result is not obvious to me. So I'm showing how little the poor quality of Indian math education, because I don't know this stuff. Anyway, so we can talk about a surjective group homomorphism. There's a bijective correspondence. God damn it! I got like the brain fog. I think it's just like this type of argument. Okay, let's work through this proof. Okay, so let's just work through this. Okay. Okay, and so working through. This is the proof of. I'm just. Anyone who's following along in the notes, I'm just labeling where we are. Okay. So proof of 2.10.4. Okay. Right. Phi inverse is not a map. Okay. What are we trying to prove? So we're trying to prove that if we pull back a subgroup, so we have a homomorphism, and we have a subgroup in the target space. Okay, and if we pull back that subgroup, it will be a subgroup in the original space, and it will contain the kernel. Okay, let's first establish that it will obviously contain the kernel. Okay. Okay, see, I wanna think about this as like, okay, let's just read the proof. Okay. Well, should I let me try to work through it logically and try to figure it out on my own before I read it. So it's believable that it's a subgroup, and if you just think about it, it's probably a subgroup. Like probably if you pull back a group, it's a subgroup. Okay, so let's suppose, okay, so H is defined as the pullback of curly H. Okay, so let's show that it's a subgroup. Okay, so let's suppose H and H prime are in H. Okay. Okay. So is it true? Let's do the closure property. So is it true that H prime is in H? Well, if we take so if we take phi of, this is equivalent to phi of H prime in curly H. And this is true because here, okay. H and H prime are in H. First we have to show this. Equivalently, okay. Equivalently, phi of H is in curly H, and then phi of H prime in curly H, and the fact that we also need to keep in mind that curly H is a subgroup of curly G. There we go. I'm getting better at the curly H, and my curly G is still a little rough. Anyway, so now we need to show that H prime is in G. Equivalently, phi of H prime is in curly H. Okay, but by the fact that phi is a homomorphism, this is equal to phi of H prime. Okay, and both of these are in H, and H is a subgroup, so yes, okay. Okay, and then we also need to show that, well, 1 is in H. Sure, that's true because because 1 is in curly H, and when we pull it back, 1 is in curly H, so when we pull it back, the pullback of anything that contains 1 will contain the kernel, so we pull back a subgroup, it will always, the set that we pull back, the set that we get from the pullback will always contain a kernel, or will always contain the kernel of the map. So yeah, sure. Yes, that's obvious. And then if H is in H, we also need to establish that H inverse is in H, non-curly H. Okay, so equivalently, phi of H inverse is in curly H. Okay, and then this is equal to phi of H inverse in curly H. These two conditions are equivalent. That's what I meant. Okay. And then this is true because curly H is a subgroup. Okay. So we've established, okay, cool. We have established that non-curly H is a subgroup of G, a subgroup of G that contains K. Sure, okay. Okay, and then the other aspect of this was if curly H is a normal subgroup of G. Okay, so let's look at the normal condition. So what does normal mean? Normal means that for any G and G, okay, I think the better way to think about normal is, instead of that GHG inverse bullshit, that it's left that for any element in G, that when you take its orbit okay, here's the way I'm going to prefer to think about this. Normal subgroup. Okay, H is a normal subgroup of G if, two ifs, so precisely when G acts on, G acts on H, G acts the same on H, using right or left multiplication from the right and the left. And the left. I.e., if G is in G, then G times H, so which is the set of all GH for, okay, and let me just clarify what this means. This is GH, G is fixed, where H is in H, okay? G is fixed. This is equal to the set. It might not be equal for every particular value H, but all it does is this is equal to H times G. So the action of G on H, its orbits, so yeah, the action of H the action of G on H, it doesn't matter whether you do it from the right or the left. That's what matters. Okay. So now let's suppose, so I think now we get to suppose additionally that H is a normal subgroup of, let's work on my curly G. There we go. That's pretty good. So H is a normal subgroup of curly G. And now we want to establish that H is a normal subgroup of G. Okay. Now, want to establish that H is a normal subgroup of G. Okay. Now, what does this mean exactly? Let's suppose gamma, I'm going to use Greek letters. Gamma is in curly G. Okay. Then gamma times, for all possible gamma, it is true that gamma acting on H, you get this sends H to some other subgroup. This is equal, it gets sent to times gamma. Okay? Okay. Okay. So, and we know this for all gamma in G. We know that this is true. We want to show that for all G in G, it is true that G times H is equal to H times G. So my instinct is to just take the homomorphism of both sides. Okay? So let's start with some fixed G in big G. Okay? Let's start with this. Okay? And what we're going to do, and we know, and okay, and we're going to ask what is phi of GH, and just to be clear, what I mean is phi of GH, where H ranges over H. I want to emphasize this is a set. Okay? So, phi of GH in curly G, where H is in H. Okay? Phi of G times H is this. Okay. Now, okay, certainly it will be true okay. Okay. Okay, so I think it will be easier algebraically to show that. Okay, I can see now why it's stated as. Okay, let's instead try to prove that G inverse is equal to H. So what this means is we take the orbit on the left by G, and then the orbit on the right by G inverse. So we act on it on the left by G and on the right by G inverse, and it might shuffle some things up, but ultimately we'll get back to the original set. Okay, so we apply conjugation to, so we have a subgroup, and then we have G act on it by conjugation, and it doesn't change it. That's another way to think about this. Okay, want to prove, so need to show. Okay, So let's take phi, and I just want to emphasize, this is equal to the set of all G, H, G inverse, where in G, where H ranges over H. We're talking about a set here, okay? And this is equal to H, okay? Okay, we want to show this. So what we're going to do is we're going to consider GH G inverse and look at its image under phi. So we're going to take phi of GH G inverse, okay? This is going to be the set of all phi of GH G inverse, okay, where H ranges over H, okay? Well, this, we can just manipulate the term inside the set. This is going to be phi of G, phi of H, times phi of G inverse, where H ranges over H. And I hope it's kind of obvious. So phi of G, let's just call gamma, let's just define gamma to be equal to phi of G, okay? This is the set gamma times curly H times gamma inverse, okay? Right. If we write out the definition of this, it is precisely this, because H is defined as the pullback. Ooh, is this where we need the surjective thing? Because now I'm... Okay, what does surjective mean? Okay, where are we going to run into trouble if we aren't surjective? We're going to run into trouble because God, where are we going to get into trouble if we aren't surjective? I don't know. Okay, but H is, non-curly H is defined as everything that maps down to curly H, okay? So, this is the active, okay, which is equal to curly H, okay? Okay, I'm not sold on this logic. Let me think about this for a second. Okay. Let's read what he has to say. Okay. What are we trying to prove? I want to prove this myself, because then I'll be more convinced of it. Okay. If H is a normal subgroup of G, then... Okay. So we're assuming that curly H is a normal subgroup of curly G, so that's why we can make this deduction here. So we must keep in mind that phi inverse is not a map, and that's confusing me because I can't... Okay. Okay, the subgroup, I'm sold on the subgroup. Okay. Let's just read what he has to say. So let X and G be elements of H and G respectively. So, right, so what I was doing. Okay. Oh, okay, so you focus on a single element. That's a much better approach. Okay, so what his approach... Okay, let's do. let's forget this. Let's forget this. Or I mean, this is a good primer. Don't forget it. But the better way, what he's doing is saying, okay, let's just consider G in G arbitrarily, and then H in H. Okay, and we're just going to consider one element. Okay, and then we're going to what we need to show is that G inverse is in H. Okay, that is equivalent to phi. Okay, this is more mirrors the proof above. This is a better approach. This is phi of G inverse being in curly H. Okay, well, equivalently, phi of G, phi of H, phi of G inverse in curly H. Okay, but remember, we're proving if curly H is normal, then non-curly H is normal. Okay, but so from the fact that non-curly H is normal, you can so from the fact that curly H is normal. Okay, so we want to prove this. Need to show this. Need to show this. It is equivalent to this, which is equivalent to this, which is true. So we've shown that the thing that we need to show is equivalent to a fact that is true. So the thing, our goal is equivalent to our assumption. So, great. Okay. Yes, okay. So, we have shown, we can conclude, so, okay. We have shown that if curly H is a normal subgroup of curly G, then H is a normal subgroup of G. Now, I think the next thing we're going to show is that if H is a normal subgroup of curly G and phi is surjective, then curly H is a normal subgroup of curly G. Okay. So, and I think the reason that you need phi to be surjective is so that it's. Let me work through this again, because surjective, I think, means that the right inverse is a well-defined function. Okay, and let's just work through this. Yes, okay. So let's just work through this visually, because I can never remember. So what I'm thinking is that surjective is equivalent to there being a right inverse function, and injective is equivalent to there being a left inverse function. So what I mean by that is, let's do a different color. And let's just call this surjective-injective logic. And I can never remember which is which, and it's better to just work it out on the fly. Okay. If so, injective is going to be equivalent to there being a left inverse. And let's have a function f from just a set A to a set B, and L is a left inverse, and by that I mean L of f is the identity function on A. Okay, so in other words, what this means is that, so what injective means is that distinct elements map to distinct elements. So you never have two elements in A that map to the same element in B. Okay? So that would be the if the function is left invertible. Okay? The reason I'm thinking that is that, so let's call this A and A prime. We can mark these as f of A and f of A prime. And as long as something can be marked as f of something, then you can always trace back to what something is. If it's not injective, then f of something, well, you can't quite trace back what something is. So an example of a non-injective function is x squared when over the rationals, let's say. Right. If you have f of x equals x squared, and you say, I know that, and I know that 9 is equal to x squared, well, there's two solutions for x because it's not an injective function. Okay. Surjective would mean that there's a right inverse. Okay. So surjective means right inverse. And let's work through the logic of why that's true. And so what breaks if it's not surjective? So by right inverse, of course, I mean a function r such that f of r is the identity function on B. Okay? And note that R you can pretend it's single valued. So even if f is not injective, you just can pick a choice randomly with R, and then when you, so let's suppose that you have this situation, okay, in A. So you have A and A prime, and they go down to the same point in B, okay? This is a point B in B. Okay, R, it doesn't, so when you're trying to define what R is, you actually have two choices, but it doesn't matter. You can just pick one. So you say R is this one, and then you apply, and then you do F, and you get back to the original point. That's all that matters. Okay, and the reason you need surjective is so that this function is defined at every point in B. So surjective means sur means onto. Okay. So what this means is every point in B is the image of some point in A. Right. Okay. Okay. So I think that is where surjectivity will come up. Okay. Now, I wish I could pull the. Okay, so maybe let's put a box around this surjective injective logic, because I think this is going to be important. Okay, so if H is a normal subgroup of G and phi is surjective, then curly H is a normal subgroup of curly G. Okay. So phi. Okay, let's just read Artin's proof. Okay. Let's suppose that phi is surjective and that H is a normal subgroup of G. A be in H and B be in G. There are elements. Okay. I prefer using different alphabets than this. Okay. Okay, so what we're trying to prove is that supposing H is a normal subgroup of G. Okay, let's. I didn't quite understand that, so I don't think it counts as cheating. But what we're trying to prove that supposing H is a normal subgroup of G, and H is still defined as the pre-image of curly H, then curly H is a and phi is surjective. Okay, so our goal is, oh, okay, the reason you need surjective, okay, here is why you need surjective, okay. I figured it out. So let's use alpha and beta, or alpha and gamma. So let's suppose alpha is in curly H and gamma is in curly G. Okay? And our goal is to show that gamma alpha gamma inverse is in curly H. Okay? And our methodology will be to pull it back to non-curly G, use the fact that H is a normal subgroup of G, non-curly H is a normal subgroup of non-curly G. Okay, and then push back down, and then push back down. But in order to be able to do this pullback, we have to be sure that there is something that hits alpha. There's something that when I apply phi to it, when I apply my homomorphism, there's something in, okay, and so let's call this, we need to know that there is an A in H such that, phi of A is equal to alpha, and there's a G in G, G in G such that phi of G is equal to gamma, okay? And the only way we're allowed to pretend to show that these 2 points exist, or that these 2 whatever elements in the non-curly group, these are only guaranteed to exist if the homomorphism is surjective. Okay, and so we can construct, or we can say, okay, not construct, but what's the word? Construct these out of thin air and declare that they exist. We know that these 2 points exist. There exist A and H and G that have these properties. Okay, and we know that H happens to be a normal subgroup of G. That's why we need surjective, is so that we can construct these points in the proof. Okay, and I would also be interested, I want to come up with a homomorphism that isn't surjective and show that we come up with a problem. I want to think about this. Okay, that's going to be a goal. Maybe that's almost certainly going to be an exercise. Let me just look in 2.10, the exercises here. That will almost certainly be one of the goals. One of the exercises. Let H and K be subgroups of a group G. No, I don't see that. That would be that's a good exercise. So this is an exercise we're going to do. Exercise. Find a problem. If find an example if phi is not surjective. I.e., so we want a group G so we want H, a normal subgroup of G, and curly H not a normal subgroup of curly G. Okay, but anyway, going back to these original proofs, this is pretty straightforward now. We just do G A G inverse. Okay. Okay, well we know that this is in H by the fact that H happens to be normal. Gag inverse is in H because H is normal. Okay. So, ooh. Okay, and then phi of this, phi of gag inverse will be phi of G, phi of A, phi of G inverse, which is equal to gamma alpha gamma inverse, and because gag inverse is in H, this is in curly H. Okay, and so we're done. And we've proven everything in this proposition. Okay. I kind of could use a break. That was quite a... That was quite... I think... God, let's get through this. Okay, but maybe I should get some coffee. Or let me have a sip of some coffee, and let's do some light reading and not read too much into this. Okay. Let phi be a surjective group homomorphism. Okay, and the reason we're going to need surjective is so that we can pull back elements from the curly group and get elements in the, let's call it the Greek group and the Latin group. Okay, let's do from G to gamma. Okay, so we want to be able to pull elements back from the Greek group and have there be pre-images in the Latin group. All right. I gotta read more. I gotta do more of Lingua Latina. I gotta work on that. That's just hard for me. God damn it. Okay. This might be important, but it's just. Okay, this is not important. Craig telling me about some curry he ate. This correspondence theorem. Okay. Surjective group homomorphism. Okay. Kernel K. There is a bijective correspondence between subgroups of G of gamma and subgroups of G that contain K. Okay, I believe that this is plausible. Okay, and this correspondence is... Let me zoom in so you can see, sorry. A subgroup H of G that contains K, its image phi of H in curly G, in the curly group. The Greeks have curly hair, don't they? Right, I imagine Socrates has his curly hair. I know a couple of Greek people, I think they have... Do Greeks... I'm sure it's mixed. I'm sure there are Greeks that don't have curly hair, but when I picture Socrates is who I think of when I think of Greece, and now I'm only thinking about his beard. I don't know about, like, his hair. But I think about Socrates. I think about Euclid, but he was actually an Arab. He was in Alexandria, so. He looked more like a Muslim type guy. Anyway, if H and curly H are corresponding subgroups, right, then H is normal in G if and only if, okay. And that's just from the previous logic, because we're assuming here that phi is surjective, and then if non-curly H is normal, then we can conclude from the logic we just did that curly H is normal, and if curly H is normal, we can conclude from the logic we just did, even if the map is not surjective, that H is normal. Whew, okay. Alright, I'm going to need to think about this, and I'm probably going to need to reread this. I will probably reread it on my own, though. We'll see. Example, oh dear God, this one that I didn't understand. Okay, let's just say that, let's use the fact that it's a homomorphism. Okay, the group S3 has 6 subgroups, 4 of them proper. What is he trying to prove? What's his point here? The usual presentation, there's one proper subgroup of order 3, the cyclic group X, and there are 3 subgroups of order 2, including Y. The correspondence theorem tells us that there are 4 proper subgroups of S4 that contain K. Ah, okay. Is it a surjective homomorphism? 2.5.13. Let me just look. That's page 50. Okay. Was this homomorphism surjective? Yes, it is. It is. Okay. Okay. There is one proper subgroup of order 3, the cyclic group X. And there are 3 subgroups of order 2, including Y. I want to open up really quickly dominant foot, actually, because I think he has a... Okay. This is a good book. There will be a link. There will definitely be a link to this now. Anytime I open a book, I'm gonna put a link to it so that you can go buy it. This is good because he has just tons of examples of stuff. Okay. Let me. How do I zoom out? Let's try. Because what he will do oftentimes is write. Let's just... I'm just scrolling, trying to find it. What he will do is do the lattice of subgroups. That's what I want to see, is the lattice of sub. Maybe let me look in the table of contents to see where that is. I think it's one of his sections. Yeah, 66. Okay. Let's scroll down to like 70-ish. 66. That's what we want to see. Okay, lattice of subgroups. And here is S3. Okay. Here is the lattice of S3. This is what Artin is talking about, is this. Okay. This lattice of S3. Okay. Let's zoom out over here. Okay, the group S3 has 6 subgroups. Save. 4 of them proper. Okay. Here we are. 1 of order 3, and then 3 subgroups of order 2, and I think this one is Y. The correspondence theorem tells us that there are 4 proper subgroups of S4 that contain K. Hence, K is equal to 4. So I think what maybe this is saying is that if we think about it as lattices, is that if we have a surjective homomorphism, we can pull back the lattice of S3. If we pull back the lattice of S3 into S4, So maybe I should trace out the lattice of S4. That would be nice. And if we pull back the... Okay, that'll be an exercise, is to pull back the lattice of S3 and show where everything goes in S4. Because that's what the correspondence theorem tells us, is that it's going to map in a nice way into the lattice of S4. That this lattice of S3 and 1 is going to map up to the kernel of the homomorphism. And then these will... Okay, let's... This is about maps of lattices. You see why I wanted to read Dummett and Foote. Okay, so we will be... I think maybe we'll go through... After we finish this chapter of Artin, we're going to go through some stuff in Dummett and Foote as well. Dummett and Foote's a good... God damn it, where'd my pointer go? There it is. Drop something on the floor, 1 second. Ah! Okay. Okay, that's I think what we're doing here. Okay. But we're definitely looking through Dummett and Foote. Okay, phew. Correspondence theorem tells us that there are 4 proper subgroups of S4 that contain K, since the order of K is 4. Okay, the order of S4 of... Okay. The group S3 has 6 subgroups, 4 of them proper. With the usual presentation, there is 1 proper subgroup of order 3, the cyclic group X, so this is X over here, this 1, 2, 3. There are 3 subgroups of order 2, including Y. Okay. There are 4 proper subgroups of S4 that contain K. Exactly 4. Not more than that. There are exactly 4 proper subgroups of S4 that contain K. Since the order of K is 4, okay, yeah, look on page 51. Since the order of K is 4, there is it's from this. Okay. It's from this. He's using this statement. Yeah, okay. He's using this statement. Okay. Since order of K is 4, there is 1 subgroup of order 12, and there are 3 of order 8. We know a subgroup of order 12, namely the alternating group A4. That is the subgroup that corresponds to the cyclic group X of S3. So A4 in this... Okay, the subgroups of order 8, which I think are going to be for D8, can be explained in terms of symmetries of the square, with the vertices of the square labeled as in the figure below. A counterclockwise rotation through the angle pi over 2 corresponds to a 4-cycle 1, 2, 3, 4. Reflection about the diagonal through the vertex 1 corresponds to the transposition 2, 4. These 2 permutations generate a subgroup of order 8. The other subgroups of order 8 can be obtained by labeling the vertices in other ways. Okay, so now this book is starting to heat up. I'm liking this, because this is what reading a math textbook feels like. Your brain being on fire. This is starting to heat up. Alright. Subgroups of order 8 can be explained in terms of symmetries of a square. So the dihedral group is what this is. Okay. Counterclockwise rotation through an angle pi over 2 corresponds to the 4-cycle 1, 2, 3. Yeah, okay. Flexion about diagonal is a transposition. Okay, and so it's something like this. The other subgroups can be correspond by labeling. Okay, so anyway. I think when we read Dummett and Foote, we'll get more into this. There are also some subgroups of S4 that do not contain K. The correspondence theorem has nothing to say about those subgroups. Okay. Proof of the correspondence theorem. This is really short, so I think we'll get through this and then we'll get out of here. All right. Let H be a subgroup of G that contains K, and let curly H be a subgroup of curly G. We must check the following points. Phi of H. Okay, let's read through this carefully. Okay. Oops. Phi of H is a subgroup of curly G. Okay, let me, it's going to be helpful to, where the correspondence theorem is on the, it's at the bottom of page 62 and the top of page 63, so keep that, I think it'll be helpful to keep that as a reference, to keep looking at that. Okay, so H be a subgroup of G that contains K. Phi of H okay, so we aren't saying that we aren't saying that non-curly H corresponds to, yeah, that's ridiculous because we're constructing them as being arbitrary. Okay. Phi inverse of H is a subgroup of G and it contains K. H is a normal subgroup of G if and only if phi inverse, okay, sure. And the bijectivity is that, okay. Okay. Sure. And then phi, okay. Since phi of H is the image of the homomorphism phi sub H, it is a subgroup of G. Yes, since it's the image of a homomorphism, it is a subgroup. Okay, the second and third bullets form proposition 210.4, which I think is what I spent all that time proving. Yes. Okay. And that's on page 62. Let me write that. So 62. Page 62. Okay. And correspondence theorem, here I'll highlight this. This is page 62. Okay. So the second and third bullets are from that proposition, which let's just recap. So we're trying to show that if we have an arbitrary subgroup down in the below, we can pull it back up and it will be a subgroup. Okay, yes, we established that, and it will contain the kernel. Okay, let's do some checkoffs. Okay. God damn it. Did the fucking, what happened? I think it opened up another window. Damn it. Son of a bitch. Okay, kill this. Fuck off. Don't ever do that shit again. What a piece of shit program. It goes in full screen mode and then can lock me out of the program. Unbelievable. Anyway, okay, so from our okay, this is just true because homomorphism. This is true because the logic we just did before. Yes, and I don't even remember what that logic was. This I think we'll want to, I'm going to want to rewatch this video afterwards. H is a normal subgroup of G if and only if phi inverse of H is a normal subgroup of G. And this is true because we assumed this is yes, and because phi is surjective. This pen is way too bleedy. Let's go down. Bijectivity. Okay, this bijectivity, I don't actually know about this. Okay. This is just true of a surjective function. Okay, so you pull back, you take a pre-image and then, right, if we go, God motherfucking damn it. So let's go to our injective surjective logic here. Okay, so when we do our phi inverse is not the same thing as R. R is a real function in this picture here, but phi inverse would be looking at B and then finding, okay, phi inverse would give us this. So if this is phi inverse of B, okay, and here is B, okay, and then if we pull back and then push back down, you get the same thing. Okay, so this is just true because it's a function. Okay, and then we take H and we push it back down, and then we pull it back, and what we're going to have to show is that we don't get any additional points. Okay, or something like that. Okay, and this is, yes, this is correct. This is correct. Also, H, okay, so first he shows this relationship. Okay. Yeah, I want to, yeah, so this is what I just said. We're going to have to prove that there's no additional points. So we push down into H, and then now we're pulling back. So we start with some, okay, if we go back to our logic before, I pick some points over here in A. So let me, so I have some points over here in A. Okay. I'm pushing them into B. Okay. And we're using into B, and then pulling them back up into, you know, this is phi inverse, and I'm pulling them back into A, and I'm obviously going to get all of the things I originally started with, but I might get more stuff if it's just an ordinary function, but the additional constraints we have on the function will say that actually no, we're going to get back exactly the original elements of A that we had. Or this is G and this is curly G. Sorry. You get what I'm saying. Okay. The only thing to be remaining to be verified right is that we get nothing else. So H is a superset of this. So let X be an element of phi inverse of phi of H, and we're going to show that X is in H. Right, okay. Son of a motherfucker. There we go. Okay. Right. So this is what I just said. Let X be an element of phi inverse of phi of H. We must show that X is in H. By definition of the inverse image, phi of x is in phi of h. Okay. Whoa. Let me zoom out so I can see the whole thing. So this is you know what I think? I was talking, so this is funny. My brain needs a little bit of a break for a second, so I'll tell you this story. Back on the original podcast I did with Craig Cannon, it's on BitChute and Rumble. It's on the Craig Cannon. There's a link in the description to the Craig Cannon Clips channel. It's in that. I think it's called The Shocking Truth About Set Theory. It's 3 parts of that video. It'll be on that channel. And there's not very many videos on that channel, so I gotta upload more videos over there. But what was I gonna say about that? We were reading Munker's topology in that video, and I was surprised because Craig was reading the book linearly. It was me and Craig Cannon, and Craig was reading it linearly, and I don't read linearly, and I think it's from spending years and years reading math textbooks. You don't read a math textbook linearly. You have to just jump around like this, right? It's always going to make a lot of... It's more like reading code. It's not like reading a book. It's more like reading code. And it's C++ minus the constraint it has to compile, right? Okay. And there's so much hidden context. Right. Anyway. That C++ minus the constraint it has to compile is like exactly what math is. Okay. Phi of x is in phi of h. Okay. So we're trying to show, maybe I'll work out something over on the side. Okay. Motherfucker! What a piece of shit fucking program. That's actually i3, which I normally love, and that, okay, so I'll forgive i3. I'm not going to forgive shitty programs. I'll forgive good programs like i3. i3 is wonderful. i3 is the window manager I use. I recommend it. It's very, very good. Okay. I will forgive i3. I will not forgive shit programs. I'll forgive good programs for doing shitty things, because mostly because I have enough experience with i3 that I understand exactly why it did that, and then I'm like, okay, yeah, no, I understand why it did that because I just told it to do that, and it's doing exactly what I said. I don't understand the way these complicated programs work, like, fucking MyPaint and GIMP, and fucking Zernal, however the fuck I'm supposed to pronounce that. I fucking hate these programs, just mostly because I don't understand how they work, and then so when it does something that I don't expect, I'm like, what the fuck, and I get mad at the program. It's a computer, it does exactly what you tell it to do. And, so anyway. It's not like it has a random number generator in there where it like says, okay, I'm just going to do something randomly. I mean, it has bugs. Zernal has bugs. That is annoying, the bugs. And then MyPaint is kind of slow, but it's not buggy. It's just slow sometimes, kind of clunky. But I'm very impressed with MyPaint. I actually really like MyPaint. And Zernal's kind of, but you know what? It's good. I like it enough that I'm using it, and that I have a video series where I use it every day. So anyway, let's get back to reading. Okay, so we're trying to show. So we need to show phi inverse of phi of h. Okay, so this is where we go this way and then back. Okay, is equal to H. Okay. And the way you show sets are equal typically is you show both the subset and the superset relationship. Okay. H being a subset of phi inverse of phi of H. This is just obvious, or it's trivial in the math sense, because, right, it's like, how do I say it? Me and my 3 friends are all traveling to Dubai, okay? We all travel to Dubai, and then what you do is you make a list of all the people who traveled to Dubai. Obviously that list is going to include my 3 friends. Me and my 3 friends. That's what this statement is. Okay, and what we're now trying to show is that the only people who travel to Dubai are me and my 3 friends. So in particular we're trying to show H is a superset of phi inverse of phi of H. Okay. Okay. And so the way we're doing this is we show, right, so now we're going to show X, we're going to pick an arbitrary element, and X is in phi inverse of phi of H, and we're going to show, need to show X is in H. Okay? By definition of the inverse image, right, because X is in phi inverse of phi of X, by definition, phi of X is in phi of H. Okay. So, therefore, there exists, I'm going to use standard math shorthand, sorry. There exists, he's going to say A in H, where phi of A is equal to phi of X. Okay? Then well, A inverse X, right, phi of A inverse X is going to be phi of A inverse times phi of X, which will, yeah, so phi of A inverse X is in the kernel of phi. Okay. Yes, sure. And since, okay, kernel of phi, which is a subgroup of H. And since H contains K, A inverse X is in H, so therefore, what is it? X is in H, so A inverse X, X inverse, well, X is in H, X inverse, this is going to be in H because, okay, I can finish this off. X is in H, so therefore X inverse in H. Okay, yeah, so we're going to need to use, yeah, I knew we were going to need to use the group properties to show this. Okay, so X is inverse is in H. Okay, well, this is a product of something in H with something else in H. So this is A inverse in H. So therefore A is in H because A inverse inverse, H is subgroup. Okay, yes. Oh, wait, what are we trying to show? No, my apologies. A was the thing in H, my apologies. Yeah, so A inverse X is in H. A inverse, say, I just got screwed. I just was thinking X was the thing in H, but no. A inverse X is also going to be in H because A is in H, A and H. So this is a product of something in H with something else in H, so therefore the result will be in H. X is in H. Done. Okay, and then the last bullet point, I don't know, that's not obviously, it seems like that should be true, but it's not quite obviously obvious why that's true to me. But I'm going to think about that, and maybe in the next video we'll try to prove that. So I'll leave you with that exercise. So it says we'll leave the proof of the last bullet as an exercise, which is the size of phi inverse of H. Well, okay, well, wait a minute. Let's think about this for a moment. This is going to be like the counting formula. So let's look at the counting formula. So the order of a group so this is a group G. Okay, yeah, this is just a corollary 2.8.13. The first bullet point. Corollary 2.8.13, first bullet point. Bullet point. And the rest of the correspondence theorem. Okay. Whew. Okay. I will try to remember. Okay. You know what? I'm gonna forget. Okay, and then you can see this is already getting fucking huge because it's taking like a minute to save this, and I have a beast of a machine. Okay. Convert ORA to PDF. I want to convert this to something that locals will only let me do images or PDFs. It won't let me try an ORA file, and then it'll probably have some stupid fucking size limit that I'm gonna break because I have this fancy monitor. Locals sucks. I'm gonna do my own thing pretty soon. So anyway, that's all I have right now. So anyway, thank you. I think that's anyway. Thank you for watching. That's all I have. This one was a lot of fun. I'm happy I did this. And I will glue the previous botched thing from yesterday on the beginning of this. Anyway, thank you for watching. Have a nice day. I'm now in a good mood. 7 a.m. All right. Happy Sunday. Founder loves you. Good morning.